This is a strange intuition, but I like it. I don't know why I like it. So imagine that we have a two-dimensional surface. So forget about qubits. Just pretend this is continuous. All right. So it's a two-dimensional surface, and I've cut some. There's a boundary out here, and I've cut some holes inside. Piece of paper. Now what we do is we draw pictures on this. So our quantum states are going to be pictures on this surface. So like this is one picture. I can put a ket sign around this. This is another ket sign. Okay, that's another picture. So these are called string nets. And basically what I'm allowing here is only cycles, but I'm also allowing the cycles to overlap each other. So I'm allowing degree 2 or degree 4 vertices, I guess. That's 2. Okay, so now my error correcting code is going to be here. It's going to be ket this plus ket this plus ket this. It's going to be a uniform superposition over every picture. So of course there's infinitely many pictures, so let's pretend that makes some mathematical sense. Right, so that'll be my encoded state. All right. This is too.
What was the degree?
Degree 2 or degree 4.
Just the number of lines coming into a vertex.
Yeah, but it's continuous, so there aren't really vertices. But yeah.
I guess this is
one.
Yeah. But yeah, so you can't have degree 1. Like you can't have a line end. It has to be a cycle. That's the only thing I wanted to show. And basically, so the reason for that is I want something that's sort of I want something that's sort of topologically invariant. So I want to be able to slide things around and not change things. And I also want something that's sort of scale invariant. So if you zoom out, it doesn't really change what you're looking at. So if you look at the uniform superposition over all nets like this, and you zoom out, it still looks roughly the same. It's just a mess of cycles like that. Whereas if I allowed like cycles to end, so I guess it's not a cycle, it's just like a segment. You zoom out, it sort of disappears, and it goes bad. So this is nicer. All right. I think there's probably some deep things you could say there, but I'm obviously not a deep thinker. So now let's discretize it. So let's get qubits. So what we're going to do, instead of the continuous circuit, I'm going to continuous surface. I'm going to put a two-dimensional lattice like this, and then so like this red cycle becomes this discretized red cycle. And now you can think of this as being qubits. If there isn't a cycle, you call that 0. If there is something, you call that a 1.
Can you say that again? If there isn't what?
Yeah, I don't know what you call it. So if you have a string, like the red thing,
Yeah.
you call that a 1. If you don't have a string like here, you call that a 0.
Okay, so you're talking about the edge.
Yeah, on the edge.
Okay.
Yeah, so the qubits aren't at the vertices. The qubits are on the edges.
Okay.
Exactly.
Their states are defined by the cycles. The
Yeah.
qubit state is defined by the cycles.
Yeah, and since now it does make sense to say ket this, it just means ket of 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, and so on. So some big string. Some big string. Okay. All right, so this is my code, and so let me show you how we get different encoded states. So for example, if I have 3 holes, I claim that this is going to give us at least 3, maybe more. Let's see, at least 3 encoded qubits. All right, so this is going to be encoded 0, 0, 0. It's just going to be all a uniform superposition over all pictures like this of cycles on top of each other and so on. And then you discretize it and find discretization. Okay, but for encoded 1, 0, 0, it'll be the same thing, except I'll have a cycle going around with the holes.
So every cycle that goes around that hole.
Yeah, plus a picture like this. So the difference between encoded 0, 0, 0 and 1, 0, 0, you get all the same pictures, except here you have a cycle that goes around, or down here you have a cycle that goes around this hole in every
Previously,
turn.
that wasn't allowed.
Yeah, and so in particular here, like if you take any path from this to the boundary, it should cross an even number of strings. Whereas here, if you take the same path, it'll cross an odd number of strings, 1 or 3 or
Okay.
5. You know, so that's how you can distinguish this from.
So it includes exactly one cycle that goes around the pole?
Well, yeah. So it doesn't have to be, right?
No,
So
it just has to be odd though.
yeah, because if you have a hole there, if you have 3 cycles like this, here's my hole.
Okay.
3 cycles like this is what I can do is I can add another cycle that doesn't change anything
Yeah.
because the superposition is over all pictures.
I
So I can add a cycle there, and then I can add a cycle that goes like this. And that will cancel out. I need a better eraser. How do I get a better eraser? See,
Oh, I see.
two in a row, two
Yeah,
things
I
cancel
see,
out.
I see.
So I'll get this,
It's always at least.
and then
one.
this is
Always
the cycle. So I can contract that topologically down to nothing,
Yeah,
and so I get 1. Yeah, so 3 cycles is the same as 1 cycle.
but 2 is.
Yeah. That's what I'm trying to say.
I see.
Yeah, and so similarly, like encoded 0, 1, 0 would mean that you have an odd number around the second hole. Encoded 0, 0, 1 would be you have an odd number around the third hole, and so on. So here's 1, 1, 0. You have an odd number around both of these. These are both in the superposition. Okay. Yeah. So this is our code, and that's a continuous code. If you want to talk about what the code looks. Okay, so first of all, let me try to explain why it's an interesting code. And I think I can explain it sort of intuitively, which is that this is like a generic term, right? So we have a superposition over all pictures, so this is just like a random picture. And the point is that, I mean, locally, it just looks like a mess. If you look at any point in here, you just see a bunch of strings. The vertices have degree 2 or degree 4, or degree 0, whatever. But you don't see any odd degree vertices, but otherwise it just looks like a mess. But globally, when you zoom out, then you can see things like this, like there's an odd number of loops around here. But these kinds of global properties only appear when you zoom out and then you look at the whole thing. And so, like the adversary, your environment can only do local changes. It can only affect a few qubits at a time. And so it can't do logic. It can't switch you from 0, 0, 0 to 1, 0, 0 or something like that. It can't add a loop around the whole cycle. It can only mess you up in a small portion. So that's sort of the idea of these. It's called topological error correcting code. That's sort of the idea of these codes. So in particular, well, here, yeah. So in terms of stabilizer algebra, in terms of the discretization, there'll be z stabilizers and x stabilizers. The z stabilizers are so the qubits are on the edges again. Remember, so the z stabilizers for every vertex you have z's around here. So it's a weight 4 z stabilizer. That enforces that the parity is even, either all zeros, or there's at exactly 2, or there's exactly 4 ones. The x stabilizers are going to be for every square you're going to have a weight 4 x stabilizer that goes like this. What an x stabilizer like that means is that you're in uniform superposition between having the square empty and adding a loop of length 4. And when you do that, that ensures that you have equal superposition over all loops. Because, like, if you take this x stabilizer and you multiply by the adjacent x stabilizer, that gives you a loop of, I guess, weight 6. So basically, you can get any loop by multiplying together these x stabilizers together. And so saying as a stabilizer means that you have a uniform superposition over all these diagrams. Right, so those are the stabilizers, and they're local stabilizers, so you can measure them just with weight 4 CAD states, I guess. The logical operators are, I've already explained these ones. So if you take x's around a cycle, that's a logical x, because it changes from 0 to 1. If you want to do logical z, it'll be a z from here to the boundary. Because counting whether the number of x's crossing from here, the boundaries odd or even tells you whether you're in 0 or 1.
So does any roots representing logical X or any root choose H representing C makes sense?
Any loop will represent some logical X. If a loop like here is equivalent to the identity. But yeah, so loops around different loops that are not topologically equivalent will give you different logical operators. Yeah, right. So here, this is x1, this is x2. If you want x1 times x2, that's equivalent to this loop. So yeah. Yeah, and then the distance of the code. So the distance of the code it's the minimum weight of any logical operator. And so here that means it's either the minimum distance around one of these holes, or it's the minimum distance from one hole to another hole, or it's the minimum distance from the hole to the boundary, whichever is smaller. So you want all the numbers to be big if you want to get a high distance code. Yeah. All right. So there's lots to say. In practice, like this is the code that people are most talking about using these days, and Google, for example, is highly committed to it. Most people with two-dimensional architectures are committed to this code because it's very naturally two-dimensional. So it takes two-dimensional locality and makes it really easy. There's lots of interesting things to say here. Like how do we do interesting gates like CNOT gates and Hadamard gates and non-Clifford gates? That's interesting. How do we do error correction fault tolerantly? That's interesting. There's lots more to say. But at least this gives you some idea of what the code is.
Is this a kind of Tory code?
Yeah, so there's different words people use. So sometimes people call this a toric code. Usually, I guess that means when the surface is a torus. If it's just an arbitrary two-dimensional manifold with boundaries, then you call it maybe the surface code. Or you call it Gitayev's code or toric code. I don't know. Yeah. Okay, cool. Thanks.